What is up, everybody? Welcome. This is Miss Wesley. I have been so excited to get to today to our next lesson on probability. We are in the probability packet. If you have it out, you're going to turn to page 7 so you can take your notes here along with me. And today we get to combine permutations and combinations, right? We'll do a little review on deciding the big, huge question, when does order matter? If order matters, I'm probably dealing with a permutation. And if order doesn't matter so much, we're talking about arrangements that are combinations. So we'll get started in a second, but on a lighter note, on a joking side, I went outside and I'm really upset because I got mugged by 6 of the 7 dwarfs from Snow White. And I'll have to tell you, not happy, because I'm not happy. And then happy wasn't one of the dwarfs that mugged me. All right, back to the math. Let's look at number 1 and 2 on page 7. We're going to skip around this page and the next page. I was thinking a lot of these would be good for you to try on your own, but maybe for us to talk through things together, we could just look at some of the more interesting ones to give you a head start on this review. So number 1 and 2 are both about baseball teams, but what's the difference? Number 1 just says how many baseball teams of 14 players can be formed if you have 20 players to choose from. Well, number 1 mentions nothing about positions, right? If I pick 14 people, it doesn't really matter who I picked first, second, and third. I still have that same team. So I'm going to use a combination for the first one. We're picking 14 out of 20 baseball players. And I think I have this already, but let's just go through the steps real quick for 1 or 2 of these. We'll do 14, or I'm sorry, the 20 goes first. So 20, math, probability, and there it is, NCR for combinations, and I'm picking 14. So let's see how many ways. 38,760 ways. Okay, not too bad. In the follow-up, in number 2, it says, now you've got your 14 players, you're picking a starting lineup, and I'm wondering if the order is going to matter. Well, keywords, starting lineup, batting order. You see the word order there. I'm feeling a permutation for this one. In baseball, the order is going to matter because their strategy, right? So picking who's going to bat when, and a different order would make for a different lineup. So let's use a permutation, which in this one we're just picking from 14, and we're making a starting lineup of 9. A 14P9 should do the trick. And I keep having to move myself. We'll go 14, same menu, probability, but the second option, 9. And there are a lot more permutations because order does matter here. So 726 million, 485,760. See if that's what you got. Okay. And we'll look at the other ones on this page a little bit later, but for now, I feel like skipping around a little. Can you guys go all the way to the bottom of the page? And there's a good lead-in to some really cool questions on the second page, and it starts with number 10. Number 10 at the bottom of page 7 says you have a softball team now, and it has 15 members, but there's a little separation here. You need to pick one pitcher for your team of 9 members. 4 of your players only pitch. They don't play other positions, but the rest of the 11 players can play anything else, so they could fill the rest of the field. Now, we are talking position. It makes me think of a permutation, but not so much. Why don't we write a separate combination for the pitcher that you're choosing? We'll multiply it by a combination for the rest of the team. Once you've split it up into 2 parts, it doesn't really matter the order in which you pick the one pitcher. There is no order there, nor the order in which you pick the other members because they're all just going to be on the team, right? So we'll say you have 4 pitchers to choose from, and you're picking one of them for the pitcher. And then for the rest of the team, without regard to order, you've got 11 more players. And how many more do we need? We've already picked the one pitcher out of 9. We have the 8 remaining positions that we have to fill. This should do the trick. And I bet you know this combination before typing it in. Think logically. How many ways can you pick one pitcher out of 4 pitchers? That should be 4 different ways. You pick the first one, the second one, the third one, or the fourth. So this is going to be the number 4 times 11C8. That can go into the calculator. It's 165. For a total of 660 ways, still a lot of ways you could form this team with those players available. Let's turn the page because believe it or not, it doesn't seem like cards have a lot to do with softball, but let's talk about number 11 because it's a really good follow-up to that last question. 11 says using a standard deck of cards. I want to highlight these deck of cards questions. We've seen them before. We saw one yesterday because believe me, moving forward, decks of cards, dice, spinners, those are classic probability questions. And as we move forward in the unit, it'll just be good if we brush up on the basics for info about decks of cards. And trust me, I'm going to go more into it later in the week. But for now, we know yesterday we kind of reviewed that there are 52 cards in the deck. And out of those 52 cards, what are the suits? You've got the red suits, the hearts, and the diamonds. And then the black suits are going to be the clubs and the spades, right? Clubs, draw a little clover there, and then the spades. What did we say yesterday? This is what we're going to have to know for this problem. How many of each suit are there? And we said yesterday 13 of each suit. 1/4 of the deck, right, is each suit. So 1/4 of 52 is 13. That's the number we need for this problem because yesterday we were asked a question. I think the question was how many suits or how many 5-card hands contain only spades. And we definitely use the combination for this because if you're getting dealt cards, the order in which you get the cards doesn't matter as much as you just having the cards in your hand. So there's definitely some sort of combination involved. And it's not involving all 52 cards. It's just saying how many 5-card hands have the same suit. So you have 13 to choose from in whatever suit you're picking. And you want to figure out the ways to pick 5 of those 13. And this alone would give you 1287. But that was our answer the other day. That was for the number of specifically hands of all spades, if you designated the suit to start out with. Well, here we haven't done that, right? So there's actually more possibilities. Just like with the softball players, we had to pick one pitcher. That was a separate combination. And then we had to pick the rest of the team. Same thing here. Let's pick what suit it's going to be. So you have 4 suits to choose from. You're picking one. And multiply it by counting principles by the number of 5-card hands of the same suit. This we know is just 4. You have 4 different suits times the 1287 to get a grand total of 5,148 ways. So you have to be a little creative with some of these, especially on this page. Don't be afraid. 12 I don't think is too tough, but I'll mention this one for a second. Don't be afraid to go back to a blanks method for some of these two, just using counting principles. Really, this whole page is a review. And a woman's going out for the evening. Ooh la la. She's going to pick one of 6 dresses. I'll put D for dresses. One of 8 pairs of shoes, S for shoes. And she doesn't even know what restaurant she's going to. Lady, you got to decide. 6 dresses, so 6 dresses to choose from, 6 possibilities. Fundamental counting principle. 1 out of 8 pairs of shoes and 1 out of 7 restaurants. That reminds me of the joke of why 7 was afraid of 8 or 6 was afraid of 7, but I shouldn't tell another joke. 1 joke for each day is totally enough. 6 times 8 times 7 should be 336 ways. So we just get that one out of the way. The 13 is a great question, but the next interesting one that I really wanted to get to, if you don't mind, is 14. I definitely wanted to try this one with you and talk it through. A bag of marbles. Bag of marbles contains 4 red, 6 blue, or 6 white and 9 blue marbles, and you're picking 5 of those marbles out of the bag. And it's just, we don't need all these numbers for every part of this question, but it says in how many different ways could you pick the 5 marbles and they all be white? Now think about it. Out of the 6, order shouldn't matter here. I should have asked you guys first, right? The order in which you pick the marbles doesn't really give you any difference in what marbles you have in your hands once you've done the experiment. So we're saying out of the 6 white marbles, order not mattering, how many ways are there to pick 5 of them? So a 6C5, not using the 4 and the 9 yet in the problem, should do it for part A. 6C5, you can go ahead and type it in, or think about it. Actually, should we be able to guess this one? How many ways, if you have 6 marbles in front of you, how many ways can you pick 5 of them? Well, maybe I should think of what in probability is called the complement of this experiment. I'm not saying complement like with an I, like your shirt looks really cool today, or you're great at solving quadratic equations. I'm saying complement with an E, which means the probability of it not happening. So right now we're saying how many ways can you select 5 white marbles? Isn't that kind of like the same as the number of ways of you leaving out one of the 6, right? Picking 5 is the same as the number of ways you could just leave out one of the 6. So if you type this in, it shouldn't be much of a surprise that you get 6 here. There's 6 ways to leave out one of 6 marbles or to choose 5 of 6 marbles. In how many ways can you select 5 blue marbles? Model this one exactly how we did part A. So out of the blues, there's 9 blues. We want to find the number of ways to select 5. I'll use a calculator for this. I'll type it in 9C5 since we decided order's not mattering, and we'll go 126. And now we get to the good 2-part question. C says, in how many ways can you pick exactly 2 blue marbles out of the 5 that you chose? Exactly 2 blue. So now we're specifying we want 2 blue and then 3 that are non-blue. Notice, maybe this will involve 2 different combinations, kind of like we did one combination for the pitcher and then one for the rest of the team. Same thing here. Let's do one combination for picking the 2 blue marbles. So out of 9, you're picking 2 that are blue. So this is for the 2 blue marbles. And then we need the others to not be blue. That's the specification. So these are for the non-blue. And how many do we need? We need 5 total. So we need the other 3 to be non-blue. And how many are non-blue? Well, in the original, I think 6 plus 4, there's 10 non-blue, and we want to pick 3 of them to round it out and get the 5 more. Multiplying these 2 together, kind of like we did in previous questions, should get you the answer. Multiply, multiply, use a calculator, 4,320. And there you go. At the bottom, you got some classics down here. Password questions, true, false tests. Have you seen one like 16? I wonder what we go back to for this. Just in how many different ways would it be possible to answer a test if you have no idea, so you're just making random guesses? How many ways could you do it if the questions are true, false? So only 2 options, right? And we're saying you can't leave any questions blank because that would be a 3rd option, right? We just have 2. Well, I could write 10 combinations and it would take me so long, right? I could do 2C1 10 different times. How many ways can I pick? 1 choice out of 2. Or I could draw out 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 blanks. We could do blanks for this question using counting principle. 2 options. A 2 would go in each of these blanks. The quickest way to write it is 2 to the 10th power. There are this many possibilities, if you're just going in and guessing, to make guesses on a random true false 10 question test, and that is 1024 ways you can do that. So just using a power here. Maybe round it out with 17. How many 5-digit passwords can be formed from the numbers 0 through 9, so 10 different digits, if repeat digits are allowed and the first digit cannot be a 0 or 1? Let's try it. So I'm going to say blanks here, 5-digit passwords. The first one cannot be a 0 or 1. So how many others do we have? We have 0 and 1, and then 2, 3, 4, 5, 6, 7, 8, 9. We have 8 other different possibilities. So 8 possibilities for the first number. How many left over? Well, repeat digits are allowed. So if repeat digits are allowed, we'll have times 10, times 10, all those possibilities, times 10, times 10. So there's another one where blanks is helpful, and you have an 8 with 4 zeros, 80,000 ways you can make that code. All right, have fun looking at the rest of these questions. Don't have too much fun, and I will see you next time. Stay tuned.